the interval from minus L to L. So up to it, we have seen Fourier series expansion in the interval 0 to 2 pi, minus pi to pi, then 0 to 2L, and minus L to L. Also, we have solved some problem based on the Parseval's identity. Now, we have to go to the next topic, that half range Fourier series. Okay, so we need to understand what is going to be the half range Fourier series. So let us see the half range Fourier series. So today we'll study half range Fourier series. Okay, so in the half range Fourier series, the length of the interval is always 0 to L. Okay, so we can see, suppose I have the interval from minus L to L, or I have the interval from 0 to 2L. Okay, so if I consider half of this, either I'll be having this half or I'll be having this half. If I consider half of this, so either I'll be having this half or I'll be having this half. So better to have this half and this half, and that's why the limit for half range we consider 0 to L. Okay, so it is for the both the interval minus L to L also 0 to L is half, and for the interval 0 to 2L, 0 to L is half, and that's why we consider the half range series in the interval 0 to L. Okay, so now what are the half range Fourier series available with us? So first is half range cosine series. Okay, so again this is half range series, so it is always in the interval 0 to L. So what is the formula we have? Okay, then we have f of x is equal to a0 plus summation an n running from 1 to infinity cos of n pi x by L, equation 1, where a0 is equal to, please be careful for the formula of a half range series. So we have 1 by L, 0 to L, f of x dx, and we have an is equal to 2 by L, 0 to L, f of x into cos of n pi x by L dx. Okay, so this is the half range Fourier series. Precisely, this is the half range cosine series. Okay, and once we have the cosine series, we also have the sine series. So we have half range sine series. Okay, this is again in the interval 0 to L. So when we say half range, it is always in the interval 0 to L. Okay. Now, what is the half range sine series we have? So we have f of x is equal to, here we'll be having summation n running from 1 to infinity, as it is only sine series. So we have bn sine of n pi x by L. This is equation 1, and where we have this Bn, where Bn is equal to, we get here 2 by L integral 0 to L f of x sine of n pi x by L dx. Okay, so these are the formulas for the half range cosine series and half range sine series. So here we are restricted to use only cosine functions, and here we are restricted to use only sine function. So in the previous examples, we were deciding the Fourier series depending on the interval and the nature of the function. So here we don't have to think anything, just we have to find if it is said half range cosine series, then we have to find this. If it is said half range sine series, then we have to find this. Okay, so let us see the example based on this half range Fourier series. Okay, so we'll have an example. Okay, so we'll go with the example. Find, and it will be mentioned half range. Okay, so find half range cosine series for f of x is equal to sine x in 0 to pi. Okay, with period 2 pi. Okay, so we have solution, right? F of x is equal to sine x p defined in 0 to pi with period pi. So here, how to find the value of L? As I said, the interval is always 0 to L. So you can see the interval is always 0 to L. So whenever it is said that half range, that means the interval is 0 to L always. And that's why whatever the interval given to you, that will be 0 to L. So this interval is 0 to L. And then we have to replace L in the cosine series by pi. Okay, so here we can write, so we have L is equal to pi here. Okay, or you can also calculate from this period 2 L is equal to 2 pi. The period is, by default period is 2L. So you can calculate, but in the interval it will be always 0 to L. So you can calculate L from the interval also. Okay, and hence we can say the half range cosine series for f of x is given as f of x is equal to a0 plus summation n running from 1 to infinity an cos of nx. This is equation 1, where a0 is equal to 1 upon pi 0 to pi f of x dx, and an is equal to 2 upon pi 0 to pi f of x cos of nx dx. Okay, so see the formula for half range cosine series. So this is the formula for half range cosine series, and then we replace L by pi. So this pi will get cancelled, and accordingly we got the half range cosine series for f of x. And now we have to evaluate this one by one. So first we consider a0. So we have 1 upon pi 0 to pi, and we have sine x, the function, and dx. So 1 upon pi, this is minus cos x, and 0 to pi. So we got 1 upon pi, this is minus cos of pi, minus minus plus cos of 0. So we got 1 upon pi. This is minus of minus 1 because cos of pi is going to be minus 1 and cos of 0 is going to be 1. So we got this 1 upon pi. This is 1 plus 1. And hence you got A0 is equal to 2 upon pi. So we have this as equation. So we got the value of A0. Now we have to calculate what is AN. So let us calculate AN. And now we have AN is equal to 2 upon pi 0 to pi sin x into cos of nx dx. So what we know is sin A cos B is equal to half of sin A plus B plus sin A minus B. So we got here A0 AN is equal to 2 upon pi integral 0 to pi half of sine of x plus nx plus sine of x minus nx and we have dx. So we can simplify as this 2 and this 2 will get cancelled and we have this is 1 upon pi integral 0 to pi. So we have sine of, we can write this as n plus 1x minus sine of n minus 1x and dx. What I did here, I have taken this minus sign out. So we got this minus sine of n minus 1. Now integrate. So 1 upon pi, then you'll be having minus cos of n plus 1x upon n plus 1 minus, this will be again minus minus plus cos of n minus 1x upon n minus 1 and the limits are 0 to pi. Okay, so let us apply this limits. So I'll take the minus out or I'll write this as 1 upon pi cos of n minus 1x upon n minus 1 minus cos of n plus 1x on n plus 1 and the limit is 0 to pi. Now apply the limits properly. Please be careful while applying the limits. So we have cos of n minus 1 pi upon n minus 1 minus cos of n plus 1 pi upon n plus 1 minus cos of 0 on n minus 1 plus cos of 0 on n plus. Okay, so we can have this 1 upon pi. Now what we know is, we know cos of n plus or minus 1 pi is equal to minus of minus 1 raised to n. Okay, so we have to use it here and hence we get minus of minus 1 raised to n upon n minus 1. Minus of, this will become minus, so minus minus plus, minus 1 raised to n upon plus 1. This is minus 1 upon n minus 1 and this is plus 1 upon n plus 1. Okay, let us simplify. So we get 1 upon pi. This term and this term I can combine. So I can have 1 plus minus 1 raised to n upon n plus 1. This minus I can take common and I can write 1 plus minus 1 raised to n upon n minus 1. And now I can have this together. So I can write 1 plus minus 1 raised to n upon pi. And here what we'll get is 1 upon n plus 1 minus 1 upon n minus 1. So it is 1 plus minus 1 raised to n upon pi. And this is n minus 1 minus n minus 1 upon n square minus 1. So this is equal to, this will n will get cancelled and you'll be having minus 2 1 plus minus 1 raised to n upon n square minus 1. Now we can see for this term we have to consider n, what happens if n is odd and what happens if n is even. So if n is an even, then minus 1 raised to n will become 1, and hence an is equal to, this will become 1 plus 1 2, so this will become minus 4 upon pi n square minus 1. Now if n is an odd, then minus 1 raised to n is equal to minus 1. So this 1 minus 1 will become 0, and we get an is equal to 0. So this is our next equation 3. But if n is not equal to 1, okay, because this formula is not applicable if n is equal to 1, and hence here we have to find out a1 separately. So that n is equal to 1, we have a1 is equal to 2 upon pi 0 to pi sin x into cos x dx. So it is 2 upon pi integral 0 to pi, and we have this is sine of 2x by 2 dx. So we have 1 upon pi integral 0 to pi sine of 2x dx. Let us integrate this. So we have 1 upon pi minus cos of 2x by 2, and we have 0 to pi. So this is equal to minus 1 upon 2 pi. I can have this minus sign outside, and then this 2 also outside. So we have, this is cos of 2x and 0 to pi. Okay. Now put the value. So you got a1 is equal to minus 1 upon 2 pi. Cos of 2 pi minus cos of 0. So minus 1 upon 2 pi. Cos of 2 pi is 1 and cos of 0 is also 1. So this is going to be 0. So you got a1 is equal to 0. This equation. So we got the value of an, we got the value of a0, and hence we are able to write down the half range cosine series. So we can say from equation 1, 2, 3, and 4, the half range cosine series for f of x is, f of x is equal to, so what we have, a0 2 by pi, a1 is 0, then what we have an is minus 4 upon, so this is minus 4 upon pi summation 1 upon n square minus 1 cos of nx, but this exists only if n is even. Okay, so that's why we have to be careful. This exists only if n is even. Okay, and hence we have to mention that it exists only if n is even. So n is even, running from even all to infinity. Okay, so that's how we are able to get the half range cosine series. Okay, for the function f of x is equal to sine x. So here we have to be careful while writing this series. Okay. So do you have any doubt in this example? So do you have any doubt in this example? No. Okay, that's good. So the formulas are nearly same as the even and odd function. Okay, but here we don't have the even and odd function. We are restricted to use sine and cosine directly. Okay, so let's have the another example. Okay, so we'll see one more example based on this. So we go with the example. Find half range sine series for f of x is equal to x pi minus x. 0 less than or equal to x less than or equal to pi by 2, and this will be pi by 2 less than or equal to x less than or equal to pi. Okay, so we go with the solution. Now you can see the interval is 0 to pi. Okay, the interval is 0 to pi, and it is said that half range sine series. So the value of L is going to be pi here. Okay, so let f of x is equal to x 0 less than or equal to x less than or equal to pi by 2, and then this pi by 2 less than or equal to x less than or equal to pi. Okay, so here we have the value. This is pi minus x. Okay, so we can write p defined in 0 to okay, and hence we have L is equal to okay. So now we have to find out half range sine series. So we can write directly. Hence the half range sine series for f of x is given as f of x is equal to, here we want sine series, so directly summation n running from 1 to infinity Tn sine of nx. This is equation 1. So where Tn is equal to, here we will be having 2 upon pi integral 0 to pi f of x sine of nx dx. Now we know there is a discontinuity at x is equal to pi by 2, so we have to split this integral into two parts, 0 to pi by 2 and pi by 2 to pi. And hence we have this is equal to 2 by pi integral 0 to pi by 2 f of x sine of nx dx plus integral pi by 2 to pi f of x sine of nx dx. Now let us put up the value of f of x in this interval. So we get is equal to 2 by pi integral 0 to pi by 2 x into sine of nx dx plus integral pi by 2 to pi. Here we have the value pi minus x sine of nx dx. Okay. Now we can see here we have to use u into v rule. Here also we have to use u into v rule. And once we identified that we have to use u into v rule, so we write using generalize by parts rule vk. Okay, so what we are able to get is C, hence we get Bn is equal to 2 upon pi. So for the first integral, x remains as it is. The integration is minus cos of nx upon n minus the derivative of this term is 1 and the integration is minus sine of nx upon n square, and this is from 0 to pi by 2. Now we have to be careful here. So for this integral, what we'll get is, see, pi minus x remains as it is, minus cos of nx upon n minus the derivative of this term will be minus 1 and the integration minus sine of nx upon n square, and the limit for this integral is pi by 2 to pi. Okay, so here we apply the limits, and hence we have okay. So we have here the limit. This is equal to 2 upon pi. Okay, for this integral, for that we have to write pi by 2. So it will become minus pi by 2 cos of pi by 2 n cos of n into pi by 2. This will become minus minus plus 1 upon n square sine of n pi by 2. Now if you use 0, this x is there, so this term will be 0 and sine 0, 0. So we'll have this much only for the first integral. Now for the second integral. So if I use pi, this pi minus pi becomes 0. Right, it's minus minus, but if I use pi, then we have sine of n pi, then again it will become 0. So this integral becomes 0 at both the terms will become 0 at the upper limit pi. Okay. Now we have to think of what happens at pi by 2. Okay. So let us think of pi by 2. Now if I put pi by 2, what I'll be having pi minus pi by 2. So it will remain pi by 2, and then this is again minus here. So minus pi by 2n cos of n pi by 2. But you are using lower limit, so this minus minus will become plus. Okay. Then this minus minus minus, and you are using lower limit, so it will become plus. So we have 1 upon n square and sine of n pi by 2. Okay, so let us simplify this. So we have 2 by pi, then we get here this is minus pi by 2n cos of n pi by 2 plus 1 upon n square sine of n pi by 2 plus pi by 2n. So you'll be having plus pi by 2n cos of n pi by 2 n pi by 2 plus 1 upon n square sine of n pi by. Now see, this term will get cancelled with this term. This term and this term will become twice. So we get 2 upon pi, and this is 2 upon n square sine of n pi by 2. So we get the value of Bn here. So Bn is equal to 4 upon n square pi sine of n pi by 2. That's what we'll be having here. So this is equation 2. Now we can write from equation 1 and 2 the half range sine series for f of x is. So what we have, f of x is equal to, so it is 4 upon pi is a constant, then summation n running from 1 to infinity. Here you have 1 upon n square sine of n pi by 2. This is a coefficient, and the term we have sine of x. So this way we are able to find the half range sine series for the function f of x. So in sine series, we just have to calculate Bn. In cosine series, we have to calculate a0 and an. Okay. So as we used to do in even and odd function, but here you don't have to check even and odd. Here you have to just find the sine series or the cosine series, whatever is required. So I hope you are able to understand this both the problems. So whatever we have seen up to 8, these both the problems and the formula for the half range sine and cosine series. So do you have any doubt in this two examples or in this topic, that half range sine series and half range cosine series? Okay, that's good. So for it all. Okay, so you don't have any doubt. That's very good. Okay, let's have another example based on this. Okay, so let's try another example based on half range sine and cosine series. So we'll go for the another example. In uh, half range cosine series for f of x is equal to x, where 0 less than or equal to x less than or equal to. So here we have the function f of x defined. So wait, f of x is equal to x be defined in the interval 0 to 2. And hence what we have L is equal to, so we got the value of L is equal to 2. So we can write the half range cosine series, because here we want the cosine series. We can write the half range cosine series, okay, for f of x is given as f of x is equal to a0 plus summation n running from 1 to infinity an cos of n pi x by 2. Remember here the value of L is going to be 2. So this is equation 1. Then we can have where a0 is equal to 1 by 2, 0 to 2, f of x dx, and an is equal to by 2. So this 2 by L we have, but the value of L is going to be 2. So 2 by 2, 0 to 2, f of x cos of n pi x by 2 dx. So now consider a0 is equal to 1 by 2, 0 to 2. This is the value of function we have x, and this is dx. So 1 half, we have x square by 2, 0 to 2. So we have 1 half, okay, and then this will be 4 by 2. So we have 1 half, and this is 2. So we get 1. And hence here we get the value of a0 is equal to, so the value of a0 is 1. So we got here the value of a0 is 1. This is equation 2. Now we have to consider what happens to an. So we have an is equal to integral 0 to 2 x into cos of n pi x by 2 dx. So you can see here the value of function is x. This 2 by 2 will be 1, and hence we get the formula for an, this. Now what we know is this is going to be u, this is going to be v, and hence we have to use u into v rule. So we say using generalize by parts rule, we get. So what we get here, an is equal to x remains as it is, the integration of cosine. So here we have sine of n pi x by 2 on n pi by 2 minus the derivative of this term is going to be 1, and the integration of this term is going to be minus cos of n pi x by 2 upon n pi by 2 bracket square, and the limits are 0 to 2. So what we know here, since for this sine term, So sine of 0 is equal to, if I put x is equal to 2, I'll get sine of n pi, and that is going to be 0. So that is the sine terms in both equation vanish at 0 and 2, and hence we have. So what we'll have here, an is equal to, this minus minus will become plus. So this 2 upon n pi bracket square being constant, and you have cos of n pi x by 2, and this will be from 0 to. Now let us evaluate. So we'll be having 4 upon n square pi square. This will be cos of n pi minus cos of 0. So we have 4 upon n square pi square. Then this term cos of n pi is minus 1 raised to n minus 1. So you got an is equal to 4 into minus 1 raised to n minus 1 upon n square pi square. So now as we know, if we encounter with the term minus 1 raised to n plus or minus 1, or 1 plus or minus 1 minus 1 raised to n, then we have to consider what happens if n is an even. Then what will happen? Minus 1 raised to n is equal to 1. So you got an is equal to 0. So this will be 1, minus 1, 0. Now if n is an odd, then what will happen? Minus 1 raised to n is equal to minus 1. And hence you got an is equal to. So you'll have here, this is minus 1, this is minus 1, so minus 2, and you'll be having minus 8 upon n square pi square. So this is the equation 3. Now we got a0, we got an, and once you have a0 and an, you are able to write the half range cosine series. Okay, so a0 we got, an we got. So let us write the half range cosine series. So we can say from equation 1, 2, 3, and sorry, 1, 2, and 3. So from equation 1, 2, and 3, the half range cosine series f of x is equal to, that is 1 minus 8 upon pi square summation. When this summation exists, n is odd. So 1 upon s n square cos of, here we have the term L is going to be 2. So it is going to be cos of n pi x by 2. Okay. So we can write here x is equal to 1 minus 8 upon pi square summation, n is only for odd, 1 upon n square cos of n pi x by 2. So this way we are able to find the half range cosine and sine series. Okay, so here we got the half range cosine series and half range sine series. So, do you have any doubts in this example that what we have seen the sine series and what we have seen the cosine series? So, up to it, we have seen about the Fourier series. We have seen about the Fourier series in the interval 0 to 2 pi. We have seen the Fourier series in the interval minus pi to pi. We have seen the Fourier series in the interval 0 to 2L. We have also seen the Fourier series in the interval minus L to L. Then we have seen the Fourier series the interval 0 to L, that is the half range sine and cosine series. So half range sine series and half range cosine series. So when you are restricted to use only the sine function, or when you are restricted to use only the cosine functions, okay, then how we are able to get the different components of the signal, and the coefficient gives us up to what extent that components are present in the signal, and hence we discretize this signal into their different components by using Fourier series expansion. Okay. More than this, we think of the components. If I want to express this in a continuous form, then we go for the Fourier transform. And this is how the first or basic step towards the Fourier transform is Fourier series. So, if we are able to understand the discrete form, then definitely we are able to understand the continuous form. So, one form we have already seen, the Laplace transform is a continuous form, but it takes the time signal to the frequency domain. This Fourier gives you the component analysis. Fourier series gives you the component analysis for any function or any signal in the discrete form. Okay. And Fourier transform takes it to the continuous form. Okay. So this way we build the base for the transform. Then one more transform we'll see, the Z transform. That is also for the discrete function. When you have the function itself is a discrete